So let's start by looking at prime numbers, and we know that prime numbers are numbers which can be divided by 1 and itself. So let's look at this list of example of prime numbers: 2, 3, 5, 7, and 11. Let's take 3 for example. We know that 3 can be divided by 1 and 3, which is itself. So therefore, we consider 3 as a prime number. However, if we consider the factors of 4, and 4 can be divided by 1 and 4, which is itself, but it also has an extra factor of 2, right? So we consider 4 as a composite number. However, if we look at a very special number of 1, we consider that as not prime because 1 can be divided by 1, but itself is also 1. So we're a bit confused here. And as well, there is also no such thing as a third factor, so therefore it is also not composite. So therefore, we just say that it's not prime, and we will not include 1 in the list of prime numbers. Next, express 3, 2, 4 as a product of its prime factors. So we set up this ladder method, alright, for this purpose of prime factorization, and we use a process of repeated division. Alright, so we will divide numbers with its prime factors. So 3, 2, 4 being an even number, we'll start by dividing 3, 2, 4 by 2, and we are going to get 162. Alright, if we divide by 2 again, we're going to get 81, and divide by 3 now because 81 is an odd number, and then we're going to get 27. And then if we repeat this process of division, we're going to work towards getting a 1 in the end. Alright, and when we arrive at 1, we stop this process of repeated division. So we basically have 3, 2, 4 equals to 2 times 2 times 3 times 3 times 3 times 3. Alright, and mathematicians like to simplify things and summarize it as much as possible. So since we see 2 of these 2's, we will put 2 to the power of 2. And since we see 4 of the 3's, we will put 3 to the power of 4. Next, let's look at how to find the highest common factor, HCF, and lowest common multiple, LCM, of two numbers. We can use listing or some primary school method, but those methods could be inefficient because numbers could be very big, or it could already be expressed as a product of its prime factors. So therefore, we can't use our primary school methods. So therefore, what you need to do is to, first of all, compare the same base to see who has a higher or the lower power. Now I'll explain the concept behind this, but you can also see that I've written down that for highest common factor, we choose the one with the lower power, and for lowest common multiple, we choose the one with the higher power. Now this appears to be opposite and sort of counterintuitive, so let's try to understand this. Right, first of all, factor. What is a factor? Factor is a number such that, let's say, 2 is a factor of 324. So 324 can be divided by 2. And we want it to be common between what? 324 and 3375. And we want it to be the highest possible. Otherwise, we'll end up with a factor of 1. And we will always end up with a factor of 1 because 1 can be... 324 can be divided by 1, and 3375 also can be divided by 1. So it's not very meaningful. Alright, so we're going to choose the highest possible factor that can divide both 324 and 3375. Now let's take, for example, these two, 3 to the power of 4 and 3 to the power of 3, to try to understand this. Now why is it we want to take the lower power? Let's take, for example, 3375. And if I were to key this into calculator, 3375 divided by 3, we clearly can divide by 3 because we're going to get a whole number at the end of it on the calculator. Furthermore, if I raise the power to 2, 3375 can be divided by 3 to the power of 2. And furthermore, if I raise this to power 3, we still can divide by 3 to the power of 3 because I'm going to get a whole number as well, and you can verify this on the calculator. So we can do that. Next, we're going to try to use our calculator to type in 3375 divided by 3 to the power of 4, and you find that the answer that you get is not a whole number. What does this mean for us? That means to say 3 to the power of 4 is not a factor of 3375, which means to say it will fail the concept of common. So therefore, we actually end up choosing 3 to the power of 3, which is the one with the lower power between the 3 to the power of 4 and 3 to the power of 3. Alright? Now what happens to base 2 and base 5? Notice that there are two blanks over here. Now one of the key thing in this method is that we want to align, for both numbers, we want to align the base, the same base, top and bottom of each other, so we can compare the powers. But when we do that, the problem is, for example, 3375 cannot be divided by 2. We're going to end up with a blank. Does it mean that there's nothing there? Not true. When we say nothing in maths, it's 0. But 0 times 3 to the power of 3 will give us 0, right? So that will be a problem. So it's not actually 0. Alright? So what happens here is that this is actually 1. Alright, and it does nothing because 1 times 3 to the power of 3 is still 3 to the power of 3. But we also know that 375 can be divided by 1. So in doing so, then we can see that actually between 2 to the power of 2 and 1 will be the one with the lower power. Actually, in actual fact, 1, you can verify this on the calculator, is actually 2 to the power of 0. So it's still in terms of base 2 and it's 2 to the power of 0. However, I'm not writing it there to confuse you, so therefore we just leave it as a 1. And likewise, the same thing for base 5. We don't see anything there. It's not nothing. It is actually a factor of 1. Alright. Once we feel it like this, it makes it easier for us to form up what is our HCF and its breakdown. So first of all, back to choosing the lower power. For base 2, I'm going to choose 1. For base 3, I'm going to choose 3 to the power of 3. Alright, and I'm not going to circle it because later on I'm going to have a problem. So I'm just going to put 1 times 3 to the power of 3. And then, of course, between 5 to the power of 3 and 1, I'm going to choose 1. Alright, so if the question says leaving your answer as a product of its prime factors or in index notation form, then we would just leave the answer as 3 to the power of 3. However, if the question does not say anything, you're supposed to evaluate it, then 3 to the power of 3 is actually just 27. Alright, next, we'll look at finding the lowest common multiple. Then we know that we are supposed to compare the same base and take the one with the higher power. So let's look at base 2. We are supposed to choose 2 to the power of 2. Alright, and base 3, we're supposed to choose 3 to the power of 4. And base 5, we're supposed to choose 5 to the power of 3. Alright, and if we were to evaluate that, that's going to give us 40500. Next, sometimes we are supposed to find a square root of a number or a cube root of a number, and earlier on, using the earlier example where we already expressed 324 as a product of its prime factors, we can use this to help us find the answer. Of course, I know we can actually use calculator to evaluate it, but sometimes a question is actually a 2 marks question and you're supposed to show the working, and then you wonder what is the working that is expected. Alright, so let's look at square root of 324 first. We know that square root of 324 is square root of 2 to the power of 2 times 3 to the power of 4. Now, theoretically speaking, that means we actually have to split into 2 equal brackets. Alright, so 2 to the power of 2 split into 2 equal brackets is going to be 2 to the power of 1 in each bracket times 3 to the power of 2 in each bracket, because it was 3 to the power of 4. And since both brackets are the same, we can basically just write 2 to the power of 1 times 3 to the power of 2 whole thing squared, and then outside there is a square root. Now the square root removes the square, then we are going to end up with 2 to the power 1 times 3 to the power 2. Now the power 1 is important because we're going to see a generalization later. So notice that after removing the square root, and I'm going to zoom into this part, notice that actually the power gets divided by 2. Alright, so originally 2 to the power 2, you divide the power by 2 and then you get 2 to the power 1. Right, next 3 to the power 4, you divide the power by 2, you get 3 to the power 2. Alright, so this generalization works for square roots, and so then after that we will evaluate 2 times 3 to the power 2 as 18. If we were to extend this a little bit for cube root, we expect a similar working like this, but I'm not going to go into that. I'm just going to go straight into the generalization. So for square root, we divide the powers by 2. For cube root, we will divide the powers by 3. So we're going to get 3 to the power 1 and 5 to the power of 1 over here for cube root of 3375. Alright, so cube root of 3375 equals to cube root of 3 to the power 3 times 5 to the power 3. Divide both powers by 3, and we're going to get 3 to the power 1 times 5 to the power 1, which is just 15 as the final answer. Next, this question is slightly more higher order in thinking. The number 324 m over n is a perfect cube. Now, remember that in the previous example, a number that can be cube rooted, if there is such a way of expressing myself, if you can cube root a number, it means to say the power obviously must be able to be divided by 3, right? So therefore a perfect cube means the power or powers is divisible by 3. Now what this means for us is, for example, 324 m over n. The problem is 324 broken down into product of its prime factors is 2 to the power 2 times 3 to the power 4. And neither of base 2 and 3 has a power that can be divided by 3. So what this question actually is testing you is whether you can see how to raise or lower the powers such that your final answer is a perfect cube, right? So in short, actually when you have times m, actually what is expected of you is to times a certain number to raise the power, and for n, when you divide by n, is to lower the power. Now the understanding of this is taught in Sec 3 where you learn laws of indices, right? So for now, you just remember times m means raise the power, divided by n means lower the power. They can change the alphabet, but the same logic applies. So next, if I were to take 2 to the power of 2, for example, if I were to times 2, clearly I'll get 2 to the power of 3. Now the problem is, why can't I just times, for example, taking 3 to the power of 4, why can't I take 3 to the power of 4 times 3 to the power of 2, and I actually can get 3 to the power of 6? The problem is there is actually a condition, and this condition is both m and n are prime numbers. Otherwise, we'll end up with different answers for different students. So therefore, this condition restricts us to certain special answers. So therefore, we can't times 3 to the power of 2, so m cannot be 3 to the power of 2. And therefore, the only possibility is for me to times 2. And when I times 2, what happens is 2 to the power of 2 times 2 will give me 2 to the power of 3, which 2 to the power of 3, the power is divisible by 3. Alright, and next, if I were to want to divide by n, if I were to divide by 3, what it does is 3 to the power of 4 divided by 3 to the power of 1. Basically, that means it's actually 3 times 3 times 3 times 3 divided by 3. And if you were to divide 3 in the numerator and denominator, you're going to end up with 3 to the power of 3, which is a perfect cube. So therefore, you realize this 2 is actually your m, and this 3 is actually your n. So therefore, the final answer is m over n is actually equals to 2 over 3. And sometimes this topic has word problems, and I know that we all don't like word problems, don't like problem sums. How do we tackle the word problems in this topic? So let's look at these two word problems. You can pause this video to read the questions for a while. But basically, after reading these two questions, you realize that basically it's just a question of, is it testing us for HCF or LCM? Then from there you can basically work out the other things that they want you to find. For example, in question 1 they want you to tell them what is the next time they flash together. But basically when you realize is it HCF or LCM, then from there you can continue working that. Now in general, if let's say looking at question 1, flashes every 40 minutes and flashes every 60 minutes, there's a certain repetitiveness to it. There's a repetition, alright? Then you realize that, for example, every 40 minutes is basically 40, right? 80, 120. For 60, it will be 60, and 120. There's a certain repetition. So therefore, when there is this repetition, what you want to be looking for is actually the LCM, multiples. Alright? Whereas if you look at question 2, the way to analyze this is, if you want to pack 150 chocolate sweets and 250 coffee sweets into identical gift bags, you're basically distributing. You're basically dividing things up. So therefore, there is that concept of dividing. So therefore, you are actually looking for HCF. Alright? One of the clue you can also get from the question is this. Now, for example, in question 2, you have the word largest. Then you start to think about highest common factor. Alright, in question 1, what's the next time they flash together? So there is that idea as well of the repetitiveness of it, the repetition. So therefore they flash a few times, and then they flash together. So there is that concept of repetition. So another type of question could be, for example, 2-person running around the track, that kind of thing. So there is that repetition. So therefore you look at LCM for question 1, and for question 2 you look at HCF. So for positive numbers, we know 1 is less than 3. However, if we were to introduce a negative to both 1 and 3, what's going to happen? Alright, so in order to understand that, let's look at the number line where I center the number line upon the 0. And if we were to look to the right of 0, we have 1, 2, 3, and so on. So clearly, as we move along the number line to the right, numbers are getting larger and larger, and conversely to the left, numbers are getting smaller and smaller. So next we look at the two numbers that we want to study, which is -1 and -3. Alright, and so now we know that the number on the right is the larger number, so therefore -1 is larger compared to -3. Alright, so therefore in here we say that -1 is greater than -3. So even though numerically 1 is less than 3, however, when we introduce a negative in, then -1 is greater than -3. So it kind of flip that inequality sign, and So it means that this whole idea of negative numbers work in reverse of positive numbers. All right. And next, let's look at multiplication operations involving negative numbers. Okay, so we know from primary school, because we only studied positive numbers in primary school, and we know that if we take positive 2, right, multiplied with positive 3, gets us positive 6. So in primary school, we took that as a default. We don't talk about positive. But here I put a positive just to illustrate the point that when we multiply two positive numbers together, we get a positive number as the result. All right. So this is for multiplication. All right. And does it work for division? It's the same thing. So if you think about it, let's say I take a 6 divided by a 2. Actually, it is a positive 6 divided by a positive 2. I will get a positive 3. So in the same way, because division and multiplications are just opposites to each other, all right? So therefore, the same rule works. So I'm not going to just change everything to division and so on and so forth, right? So from this point on, we understand that it works for multiplication, it also works for division. Next, let's look at line 2. Line 2, we have positive 2 multiplied with negative 3, and on the calculator, you will get negative 6. All right, this is a quick revision, so I don't want to go into the deeper concept of it. So therefore, if you want to go into the deeper concept, you need to look at number lines, number disks, or algebras, and so on, right? So I don't want to spend a long time dealing with that. So when we verify that, then we understand that, okay, when we take positive number multiplied with a negative number, we get a negative number. All right, so it won't be surprising for us to see that in line 3, when we multiply a negative number with a positive number, we get a negative number. All right, and so therefore we have negative 2 multiplied with positive 3 gives us a negative 6. All right, and in the last line, that's the most interesting one. When we take negative 2 multiplied with negative 3, we actually get a positive 6. So think of the two negative signs in this way. So negative is like a negation. All right, so the you can think of it this way: the first negative sign reverses the second negative to become a positive. All right, but in short, when you take a negative number multiplied or divided by a negative number, we're going to get a positive number in the end. So how is that useful to us, right? And we have this question: evaluate without using a calculator this number expression. And so obviously, if you cannot use a calculator, you will need to show some working to convince the marker that you indeed didn't use the calculator. All right. So for the purpose of this type of question, what you need to bring back is your Bodmer's rule. Right, and remember that we're gonna perform anything that has a bracket first, all right, before we deal with division, multiplication, and then later on the addition and subtraction. All right, so first I'm going to deal with the 4 minus 2 first, and that becomes a 2, and then a 5 minus 8 is going to become a negative 3. All right, next we see a number followed by a bracket. There is actually an invisible multiplication sign. All right, and then next we are good to go and proceed on. All right, we're going to do the multiplication first before the subtractions. All right, so we have negative 7, all right, minus 3 multiplied with 2, which is a 6, and then minus 4 multiplied with a negative 3, which is a negative 12. And so of course you see this over here, right? Earlier on in our previous page, we dealt with this, and then this is like a negative 1 multiplied with a negative 12. So therefore, that's going to give us a plus, all right? And we have negative 7 minus 6 plus 12. And so therefore, we are able to evaluate what this means, and negative 7 minus 6 is actually negative 13, then plus a 12, all right, it's going to give us a negative 1 as our final answer. So we look at how to round off numbers to 3 significant figures, for example, right? And in here, I'm not going to go through in detail how to decide whether a certain digit is significant or not. All right. Instead, I'll focus on two types of numbers. One is a number that is very much bigger than 1, and then the other number is very much smaller than 1. All right. So let's look at the first one. So the first one goes 589,993, and I'm supposed to round it off to 3 significant figures. So I'm going to, for illustration's sake, draw this dotted line. All right, and the first SF is 5, second SF is 8, third SF is the 9 over here. Then we need to study the fourth SF and need to look at the 9 over there. So the rule goes, if this digit, this fourth SF, is anything less than 5, then we don't need to round up. All right, anything that is more than or equals to 5 means the third SF I will need to round up. All right, so the trouble with this is that because the fourth SF is a 9, then this 9 will have to round up. Okay, so the third SF will have to round up. But the problem is, when we round up, it's not going to round up to 10, right? Then where do I put the 1, right? So when we round this up, we round this up to 0 and carry over that 1, right? Because it's supposed to be 9 round up to a 10. Carry over the 1, so 1 and the 8 adds up to a 9. So then the first SS stays as 5. This is a very common mistake where when people are told to round off to 3SF, for example, and then you just left with these 3 digits and you just conveniently discard the rest. Right? Think of it this way. In the context of money, I'm not going to round off a 6-figure sum of money to a 3-figure sum of money. So that's not going to make sense. So therefore, the other digits are all just going to become 0. All right. So a very useful understanding here is, let's look at the first SF. This digit 5 is in the 100,000s place, right? And therefore, in your final answer, it is also supposed to stay as the 100,000s place. All right. So therefore, this is a good gauge for us to know whether we are correct or not. For some people, when they leave their answer as 590, then this 5 would have become in the hundreds place. All right, which is clearly wrong, and we've changed the place value of the digit 5. Next, let's go to this number 0.009248. All right, and again, if we were to round off to 3SF, and we know that the first SF is 9, all right, and the second is the 2, and then third is the 4, and so on. The rest of these are not significant, right? So therefore, we look at this fourth SF, which is the 8, and then we realize that the 4 will need to round up. Right, so therefore, in our final answer, it will be 0.00925. Right. So earlier on that example, we put in the other zeros. So does this mean that I will need to change this to 0? The answer is no. Right? Because if you do that, what happens is you are deemed to purposely put in the 0, and therefore that 0 must be significant. Otherwise, why would you want to put there? Right? So therefore, in this case, if you put in that extra 0, this is actually for SF, because there must be a reason why you put this 0. So therefore, do not do that. And let's revisit the previous number again. Right? So what happens about all these? All these are actually not significant. They are there so that this digit 5 actually remains as the 100,000th place. Alright, so therefore there is that slight difference between these two cases, and do understand the rationale. So for simplifying algebraic expression like 4a minus 3b plus 2a minus 7b, alright, we need to understand that we have four terms over here. First term is 4a followed by 3b followed by 2a followed by 7b, and they are separated by addition or subtraction operation in between. Okay, so the next thing is we need to understand what are the like terms. Like term means they actually have the same variable, for example a and a. This means that these two terms are like terms, right? And of course a and b are unlike terms, so we're going to put the like terms together. So I'm going to move the 2a together to with the 4a, so I'm going to move the whole entire plus 2a over to join with the 4a, and then I'm going to move the whole entire minus 3b over here, alright, together with the other minus 7b. Right, so next I will focus on the coefficients. So what are coefficients? Coefficients are the number that is on the left of the variable or the alphabet you see here. So this is the variable a, and then 4 is the coefficient, right? So the number before it. Okay, and so I'm going to focus on the coefficients. Right, so I'm going to take 4 plus 2, which is a 6, and then write the a, and then the other one would be negative 3 minus 7, alright, which is negative 10, and then I'll just put in the b. Alright, so that is how we simplify algebraic expressions. Next, to expand algebraic expressions, let's look at the first one. Alright, and we need to do something called distribution. So we're going to use the distributive law, alright, or somewhat in layman term people call it the rainbow method. Right, the proper term is called distributive law, and we so-called distribute these 3 to each of x and 4. Alright, so think of it like you're giving presents, right? So you're giving this 3 as a present to x and 4, right? So we have 3 multiplied with x, so that's going to give us 3x, right? And next, 3 multiplied with 4 is going to give me a 12. Okay, next, what happens if there is a negative number outside of the bracket? So again, we still distribute this negative 2 to the other two numbers. Alright, and so remember that there is actually an invisible multiplication here. Right, so that means we're actually taking negative 2 times positive 3x. So therefore, focus on the number negative 2 multiplied with 3 is going to give me a negative 6 and an x, right? And then the next one will be negative 2 multiplied with negative 5. So remember that negative number multiplied with a negative number is going to give you a positive number. So plus, right, 2 times 5 is a 10. So let's deal with factorizing algebraic expressions. So we have the first case, or the first question, factorize 3xy plus 15x squared y. Alright, so in this type of problem, we need to identify between the two terms, are there any common factors? Alright, so therefore we can see for the numbers 3 and 15, common factor of 3 and 15 is 3. So I'm going to extract the 3. Alright, and next, right, when we extract the 3 from 15, do remember that 15 is made out of 3 times 5. So therefore, when we extract out the 3, we are left with the 5. So over here we have the 5 inside. But we're not done, because we still have more common factors. For example, I can again extract the x. Can I extract x squared? No, because the first x over here will not have enough x to be extracted, right? So think of the x squared as x times x, whereas the first one over here is just x, right? So it doesn't have enough for us to extract, so therefore we can only extract x, all right? And then we have y plus 5xy, right? Are we done? We clearly are not done, and we still can extract another y, right? But take note, when we extract out the y from here, it's not going to become nothing, right? So when we extract out a y and put it outside, we cannot write like this. Okay, this will imply that this becomes a 0, which is not the case. Recall that y is also made up of y times 1. So when we extract the y, we're left with the 1. So therefore, we still need to put the 1 next. For the advanced learners out there, you know that I'm doing it in a very, very slow fashion. So therefore, in exam, if you're able to identify the common factors at the highest possible one, then you do not need to go through all those steps, and you can straight away just leave your answer like this, right? Of course, your answer, you can move it up, but yeah, you can just get the answer in one step. All right, next, when we have a common factor, all right, between these two terms, there is a y minus 3. It is the same thing. So I'm going to extract the y minus 3 as the common factor and put it outside. And what we're left with is actually the 4x and the minus 3 here. So this itself is still a process of extraction. All right, and we call this factorization by extraction. So the purpose is to extract out the common factors. Next, for algebraic fractions, all right, it works in the same way like your primary school adding or subtracting of algebraic fractions. We need to make these two fractions have the same common denominator, and then in order to do that, actually we need to identify what is the LCM of the denominators, which is 5 and 2, right? So therefore, for the LCM of 5 and 2, it is actually a 10. So for the first fraction, actually, I will need to multiply the 5 with the 2 over there, all right? And we can't just do something to the denominator, just multiply 2 to it and ignore the numerator. We're going to change the overall value. So therefore, we are going to multiply the numerator by a 2. So in a sense, we actually are not changing the overall value. All right. Next, we will also multiply 5 to the denominator of the second fraction, right, in order to make it a 10, right? And then we'll do the same to the numerator, right? And next, we're going to simplify things first before we proceed. So therefore, we have a common denominator of 10 for both fractions, and we will have to distribute in the number that is outside the bracket. So 2 times 4 is 8, so we have 8x. 2 times 1 is 2, and then there's a minus that follows. So just a point of caution, there's a minus in between. For the advanced learner, you know what happens with that, but we will just ignore that for now. We're going to distribute in the 5, so 5 times x will be 5x. 5 times 3 will be a 15 with the plus there. All right, and next, because of the minus in between these two fractions, you need to be very careful. So what I will do to be careful is this. I will think of it as the numerators being written like this. All right, so the minus over here is going to minus the whole entire 5x plus 15 and not just the 5x. So it's going to affect the 15 as well, right? So we can actually just drop the bracket in the first two terms here, and then this is like a -1 being distributed in. So therefore, in the next step, what's going to happen is I will have denominator of 10, 8x minus 2, and then -1 distributed in means minus 5x, all right, and take note, -1 times positive 15 is going to give you a -15, so we put minus 15 over here. So do take note, right? For this, originally it was a plus, now it is a minus. So that is the effect of having that minus in between two fractions. Alright, and then finally we simplify that, and 8x minus 5x means 8 minus 5 is a 3 with the x, and then -2 minus 15 will be minus 17 here, right, over 10. So for algebraic equations, think of it as think of the word equal, that is supposed to be an equal sign separating a left hand side, which I call LHS, and the right hand side, which I call RHS. So for example, if you have x plus 3 equals to 5, you have that equal sign, alright, and as well you have a left hand side and then a right hand side, and this itself is balanced, and as you can see later, we know that for it to be balanced, that x has to be 2, so 2 plus 3 equals to 5, which is the right hand side. Alright, so some of the important things that is going to help us in solving equations and in terms of getting certain shortcuts that will help us be very fast in solving equations, need to bear in mind what some of the things that are opposite of each other. So left hand side is opposite of right hand side, alright, and you have positive is opposite to negative, plus opposite to minus, times opposite to divide, or multiplication is opposite to division, and then you also have square root opposite to square, and then cube root opposite to cube. Alright, and so next, let's look at a simple example. Let's say we are asked to solve x plus 5 equals to 8. Alright, so traditionally what we would do here would be to isolate the x, and then to do that I need to remove the 5 from the left hand side. So in order to do that, I need to think of the opposite to positive 5, right, and that is -5. So when I take positive 5 plus a -5, that forms a 0 pair, alright, and then that removes the plus 5 there. So then that means we would also need to do the same on the right hand side. Alright, in order, remember, like I say, in order for it to be balanced, I'm going to need to do the same thing on both sides. So think of it as a seesaw. Now on the left hand side, you have a person who is let's say 50 kg, and in order to balance out on the seesaw, then you need to put somebody who is 50 kg on the other side, and then also same distance away from the middle, right? So then here we have balanced the equation, and then next we will need to solve. Alright, and we solve for the x, and we get x equals to 3. Now I want you to observe this, and that is the traditional way. I'm gonna want to get a shortcut for exam. So if you look at this, we have a plus 5 there, we have a positive 5, and we see that on the other side, this is -5. So a very fast way is, if I see x plus 5 equals to 8, then the next step would be plus 5, opposite to it is -5, so 8 minus 5, and then that gives us x equals to 3. Right, I'm going to apply the same approach, but let's look at simple basic stuff first, alright, for the next example. Okay, so let's say we were to solve 3x equals to 9. Now before I go on to this, remember that it is actually 3 multiplied with x, or 3 times x, alright, and the opposite of times is divide. So in order to remove 3 times, we need to divide by 3, on both sides. So that's the technically correct way to do it. So it's 9 divided by 3. You can write it in the fraction form. And then we solve and we get x equals to 3. Now the same idea is this. If I were to take a shortcut and then 3x equals to 9, then we consider 3 times x means when it goes to the right hand side, it's actually divide by 3. So instead of 3 times on the right hand side, it becomes divide by 3. Alright, so here it is 3 times, on the other side it is divide by 3. So next we have to solve 2x over 5 minus 1 equals to 3. So here we need to be a little bit careful. Alright, we cannot just consider this as divide by 5 and then so therefore on the right hand side it's going to be a times 5. Take note that there is something extra and I'm going to point out this term as the one that is extra. So we need to get rid of that first and isolate the fraction. So first, need to consider that this is a minus 1. So we have 2x over 5 minus 1. So opposite of minus is plus. So 2x over 5 equals to 3 plus 1. So we're going to simplify that as 4. And then next, consider that this is a divide by 5. So on the right hand side is going to be times 5. So 2x equals to 4 times 5, which is going to give me 20. Then last of all, this is 2 times. So that means on the right hand side it's going to become divide by 2. And 20 divided by 2 is going to give me 10.